Okay, class, we're going to begin the second module of the course today. And we'll start with the first topic in this module, which is the second derivative. We're going to be needing the very same derivative rules that we just looked at and that you were just tested on. So the derivative of x to the n, which we use when we're differentiating polynomials. When we have a function of x raised to an exponent, so maybe a binomial with an outer exponent, we will use the chain rule. And then if we have two functions of x multiplied together, we'll use the product rule. One function of x divided by a second function of x requires the quotient rule. And again, this was what we reviewed completely in the first unit of this course. So today we're going to look at forming the second derivative of various functions, and the really important thing is identifying the function correctly. So in example 1 here, you should see that this is a polynomial. So we will simply use the very first derivative rule that you learned in this course. So the derivative of x to the n is nx to the n minus 1. So we end up with 5 times 4x cubed, which is 20x cubed, plus 3x squared, minus 3 times 2x, so negative 6x. So we end up with y prime. Notice we're changing the notation on the left. Y prime is 20x cubed plus 3x squared minus 6x. So the second derivative means the derivative of y prime, and we call it y double prime. So it will be 20 times 3x squared, so 60x squared, plus 3 times 2x, or 6x, minus 6 times 1, so minus 6, like this. And this is our second derivative. And I've been encouraging you to always common factor your answers. So in this case, we end up with this trinomial, and 6 is common to all terms. So it makes sense in this last step to remove that common factor of 6. Okay, so this was a polynomial to begin with. The first derivative, y prime, that we differentiated was also a polynomial. And you can see that the second derivative is a polynomial also. Okay, let's look at number 2. So we have functional notation. We've got a binomial now with an outer exponent. Okay, so this is when we need to use our chain rule. So u is the binomial, and it has an exponent equal to n. So in this case, u is 3x plus 2. Oops, 3x plus 2. Let me go get some white out. Give me a second here. There we go. Okay, 3x plus 2. Sorry about that. That's our u. And our n value is 3. All right, so when we use the chain rule, we know the exponent comes forward. So that will be the exponent of 3. Then we're going to have the binomial u, and we have 1 less from the exponent of 3. Then we will have an exponent of 2 here. So this is f prime at x, the first derivative. So again, the 3 comes forward. The binomial is repeated, and its new exponent is 1 less. So the new exponent is 2. So this is n times u to the n minus 1. And now we have to make sure we multiply that by the derivative of u with respect to x. And the derivative of u with respect to x is 3. So we make sure we multiply here at the end by 3. So 3 is the derivative always of the inside of the bracket. So this becomes 9 times 3x plus 2 all squared. And that's our first derivative, again, f prime at x. So the function f required us to use the chain rule. And now you can take a look at f prime at x, because we're going to differentiate it now in order to find f double prime at x. And we can see that it too is going to require the chain rule. We have the very same u here. So we've got the chain rule once again. So let's write f double prime at x equals, so the 9 is already in front. The 2 comes down and multiplies by the 9. We get 18. 3x plus 2. The new exponent will be 1 less. And again, we are multiplying by the derivative of the inside of the bracket, which is 3. Okay, so this part here, we can just sort of keep off to the side if it's helpful to you. Okay, you don't in fact have to do this here if you want to just make sure the exponent comes forward, 1 is subtracted, the derivative of the inside of the bracket is here. Okay, and then the very same thing when forming f double prime at x. The 2 comes forward, multiplies, 1 is subtracted from the exponent, and then multiplied by the derivative of the inside of the bracket. So 18 times 3 now is 54. So we get 54 times 3x plus 2, like this. Okay, so in example 1, both y and y prime were polynomials. In example 2, both f and f prime required the chain rule in order to differentiate them. So let's take a look now at the third example. I'm hoping that when you see this third example and there's a function of x on top and a function of x in the bottom, you recognize that we're going to need the quotient rule. Okay, and that u is always the numerator and v is always the denominator. So we can form u prime. What is the derivative of 3 plus x? Well, it's 0 plus 1. Form v prime. What is the derivative of 3 minus x? Well, it's 0 minus 1. And then use the quotient rule to form y prime. So v is multiplied by u prime. And from that, we subtract u after multiplying it by v prime. And that is over the square of v. Okay, so v times u prime minus u times v prime over v squared, like this. So now we'll just, simplify the numerator a bit. I'll just include this step in case it's helpful to you here. I'm going to take the -1 and multiply it inside the bracket, so it'll be a -3 and a -x that we are subtracting, right? So we're subtracting this after multiplying it by -1. So I can first bring it inside, perhaps like that. Maybe that'll make it clear. And now we're going to lose those brackets in the numerator. So here we're going to multiply through just by 1. So 3 minus x. And now we're going to have, this is like multiplication of -1. So we're going to have plus 3 and plus x. So what do we end up with in our numerator? We're going to have 3 plus 3 or 6, because the negative x and the positive x, of course, cancel themselves out when we collect like terms. So we get y prime is 6 over 3 minus x all squared. So we used the quotient rule when differentiating y. Now we're trying to find y double prime, the second derivative. Will we use a quotient rule again? Well, we can use a quotient rule again as long as we treat u as 6 and therefore u prime as 0. But that's almost overkill. It's a bit unnecessary. When this isn't a function of x, right? There is no x present in the numerator. It makes sense to just rewrite this function in this way with a negative exponent. And now we can avoid the quotient rule and we can use the chain rule. You see, we wouldn't use a product rule like on this either, although we could. If we used the product rule, we would have still u is 6 and u prime is 0, and that would work. But an easier way to do this is just now with the chain rule, since this is just a constant. So in using the chain rule, what do? We bring the exponent -2 forward. It multiplies by the -6 sitting here. So we will have -12. The new exponent will be -3. And we have to remember to multiply that by the derivative of the inside of the bracket. The derivative of 3 minus x is 0 minus 1, so -1. And so this gives us -12 times -1 is +12. And rewriting this now with a positive exponent, we would have 12 over the cube of 3 minus x. Okay, so we're using the chain rule. We're treating this like a u to the n. So again, like we did here, if you like to do that, you could say u was 3 minus x and u prime, or du by dx, is -1. Okay, so we did indeed use the chain rule to form y double prime. And as I explained, quotient rule would work as well in this form with u prime 0. Product rule would work with this form, u prime 0, but chain rule is the easiest, most direct way to form y double prime. Okay, so we're going to do one more example together, and it's this one. We're starting with the cube root of this binomial. And you realize, of course, that the very first thing we need to do is eliminate the radical. In this case, we'll have a fractional exponent of 1/3. And we're going to form f prime at x. Differentiating this, of course, requires the chain rule. So we have a u to the n here. f prime at x. So the exponent of 1/3 comes forward. The new exponent is 1/3 minus 1, or 1/3 minus 3/3, so it's negative 2/3. And we remember to multiply that by the derivative of the inside of the bracket. And the derivative of 6x squared plus 5 is 12x plus 0. Okay, so this is what we get when we apply the chain rule. All right. And so now we simplify that. So 1/3 can be multiplied by 12x to get 4x here. Okay, so the chain rule was used in changing from f to f prime. Now look at f prime. How do we differentiate f prime? Well, we have to notice now that we have one function of x here multiplied by a second function of x here. And so absolutely it's going to require us to use the product rule. This is no longer just a constant sitting out front, which would allow us to use the chain rule, but it's the presence of the x here that makes this now a product. Okay, so we're going to use the product rule. That means identifying 4x as our u and identifying this as our v. Now in differentiating v, which is a binomial with its own exponent, we will need the chain rule. Okay, let's form u prime and v prime. So the derivative of 4x is 4. In differentiating v prime, we must use the chain rule. So negative 2/3, repeat the binomial, subtract 1 or subtract 3/3 from negative 2/3. So that will be negative 5/3. And don't forget to multiply it by the derivative of the inside of the bracket, which is 12x. Simplify this. What is negative 2/3 times 12x? It is negative 8x. All right, and now we're all set to use our product rule because we have u, we have v, we have u prime and v prime established. So now we use the product rule to form, it will be f double prime at x. Okay, so don't forget the product rule. U v prime plus v u prime. U times v prime plus v times u prime, like that. Okay, take a look again. U v prime plus v u prime. Okay, take note that this term now in the front is negative 32x squared. Also, that it looks a little more natural to have this 4 in the front of the term. Okay, and now, in order to finish this, we do the common factoring. So we are going to compare the left here of the plus sign with the right here of the plus sign. And hopefully you'll note that we can either remove at this point 4 or negative 4. Okay, these things are both divisible by either 4 or negative 4. So I'm going to remove a 4. And as for this binomial, 6x squared plus 5, we removed the lower exponent, remember? So negative 5/3 is more to the left on the number line than negative 2/3. Okay, and now this is the part that many of you are finding difficult. After you identify the greatest common factor, you have to fill in this bracket. And to do that, you're essentially dividing. So you're dividing, so I can write it in here. It'll just be a little small. You're going to divide what you had by what you've removed. Okay, so this is the term on the left, and it's being divided by that greatest common factor. Then the plus sign, and now the whole thing again. So the right term underneath, the right term in the top, and underneath it goes the greatest common factor, like this. Okay? So let's now simplify this first fraction. You can see that this is identical and will cross out completely. So all we have to do is divide negative 32x squared by 4, and that's negative 8x squared. And now we put in the plus sign, and we do the division here. Here, the 4's will cancel out, and we're dividing this term with an exponent of negative 2/3 by this term with an exponent of negative 5/3. And remember, these are powers with the same base, and the rule is that you subtract exponents. So I would have right here negative 2/3 subtract negative 5/3. And of course, that's the same as negative 2/3 plus 5/3, and it's 3/3 or 1. Okay, and I've talked about this in previous video. This will always be a 1 inside the bracket if you have done your derivatives correctly and if you're removing the correct greatest common factor. Okay, but again, it's negative 2/3 subtract a negative 5/3. That's how you get positive 1. Okay. Inside here now, if we just drop this bracket, since there's no longer an exponent here except for 1, we can drop the bracket and collect like terms. So we'll end up with negative 2x squared plus 5 in there. And lastly, we can drop this to the denominator, where the exponent would be positive 5/3. So when it comes down to the denominator, the exponent is positive 5/3. And so that means we can go to radical form now that we've got that positive 5/3 exponent. The 3 will be the index, so here. And the 5 is the exponent right there. Okay, and that's the second derivative. So I think that the last two examples are highlighting the fact that the function can change. So in example 3, we had a quotient for y, but y prime itself was not a quotient, but rather a chain rule could be used on it. And then in this most recent example, the original function, f, required a chain rule to differentiate. However, when we looked at f prime, we realized that to differentiate it would require the product rule. Okay, so much more practice, I think, needed for all of you. I've identified 5 questions from your textbooks that I would love for you to try. And I have also posted my full solutions to those 5 problems for you in Blackboard. Okay? So thanks for watching, and work hard at this, all right? It'll get easier and easier the more time you spend with it. Thanks a lot.